So, welcome to separation of variables. We're going to be working in spherical polar coordinates. We'll talk about that in just a moment. But remember, in spherical coordinates, if you have a position here, a distance r from the center, then theta will be measuring from the z-axis, and the angle phi, the azimuthal angle, we measured from the x-axis. So we're going to be dealing with spherical polar coordinates, which means we're going to assume that the potential v r theta phi is actually just a function of r and theta. So no phi dependence. This is known as azimuthal symmetry. So we want to do separation of variables in Laplace's equation. Remember, del squared v equals 0. That's Laplace's equation. All right, so let's follow the 6 steps to separating out variables. 1, write out the differential equation explicitly in terms of the variables, which in this case are r and theta. So the Laplacian of v, if you look in the front cover of your book, you will see that that's 1 over r squared, the partial with respect to r, of r squared, the partial of v with respect to r, plus 1 over r squared, 1 over sine theta, partial with respect to theta, of sine theta, the partial of v with respect to theta, plus 1 over r squared, sine squared theta, second partial of v with respect to phi squared. And this is 0. It's Laplace's equation. Now, because we are assuming that there is no phi dependence, that means that this derivative is going to give us 0. Now, for the second step, we have now this written out explicitly in terms of variables. For our second step, we're going to assume that we can write v of r theta in separable form. We're going to write this a function, which I'm going to call capital R, is a function of the variable r, times theta, capital theta, which is a function of little theta. So I am going to assume that I can write these out in this way, and I'm going to write 1 over r squared, the partial with respect to r of r squared, the partial with respect to r of r times capital theta, plus 1 over r squared sine theta, the partial with respect to theta, sine theta, the partial with respect to theta of r capital theta. So when we're doing the partials here, remember that capital theta depends only on little theta, not on r, so it's going to come through all of these derivatives. So I can write this as theta over r squared, and now I can write all of these partials as total derivatives because there's only one variable now, so it doesn't matter. R squared d big R d little r, plus capital R, which is, remember, the function of little r squared over sine theta d theta sine theta d big theta d little bit theta. All right, now to step 3. Divide by v, which in this case, remember, is big R, big theta. All right, so dividing by both sides by v, this gives me, I'm also going to multiply the whole thing. So here what I'm going to do is I'm going to multiply my whole equation by r squared over v, which is big R, big theta. All right, so that will give me on my left-hand side 1 over big R ddr of r squared d big R d little r, plus 1 over big phi big theta, sine theta, d theta, sine theta, d theta equals 0. All right, what's next? Next is step 4, which is isolate the variables. We've already done this. We have just the r's on this side part and just the thetas on this part, so we're all set. Let's move to step 5. Step 5, start that on a new page. So step 5 now is to consider small changes in your variables. So r and theta. Oops, wrong way. So sorry. So now we're going to consider small changes in the variables. Let's write down our equation again. A little bit more explicitly, this is 1 over the function big R, function of little r, the derivative with respect to r of little r squared, plus the derivative of big R, remember that's a function of little r with respect to r, plus 1 over sine theta times capital theta, it's a function of little theta. Take the derivative with respect to theta of sine theta d big theta, which is a function of little theta, d theta, which is equal to 0. Now, what happens if little r changes by a little bit? It is only going to affect this left term. So this depends only on r, not theta. So in order for this equation to be true for all values of theta and phi, this must be equal to a constant for all possible values of r. And the same is true with the right term here, the second term. This depends only on theta. And if theta varies a little bit, this has to, again, or even a lot, has to remain constant. Now I'm going to make a choice. I'm going to choose this constant here to be plus L times L plus 1. We'll see later that L is going to be an integer. And that must mean that this constant, because I need to add together to be 0, is minus L plus 1. All right. 6, and our final step here is to write each equation in standard form. So standard form is going to be when you have the derivatives on one side equals some constants times other derivatives. So this is going to give us, for the left equation, 1 over r times the derivative with respect to r squared, derivative of r with respect to little r, is equal to L plus 1. So standard form would be the derivative with respect to r of r squared dr d little r is equal to L plus 1 times big R. This is the standard form. All right, let's do this again for the theta equation. 1 over sine theta times big theta d theta sine theta d big theta d little theta is equal to minus L plus 1. All right, so if I multiply both sides by big theta, I'm going to get 1 over sine theta d theta sine theta d big theta d little theta. And this is minus L plus 1 times capital theta. So standard form means that all of the functions are in the numerator, where we're used to dealing with them. All right, so later we'll see L is going to be an integer, but notice that let's consider the case where L is positive, bigger than or equal to 0. So let's say L equals n, where n is some positive number. Then L times L plus 1 is going to be n times n plus 1. Now in our second case, the second case is what if L is less than 0? In this case, let's write it as L equals minus n minus 1. Minus n is some number. Then L times L plus 1 is going to be minus n minus 1 for L times minus n minus 1 plus 1 for L plus 1. These two happily cancel, and I get n plus 1. So these are the same. So regardless of whether L is positive or negative, I can still write it in this form. So I'm going to assume that L is positive without loss of generality, because it's going to cover both negatives and positives. And in fact, it's going to look exactly the same way. All right, so next we are going to look at the radial equation. The radial equation is the equation that depends just on the radius or distance from the origin, which is r. So our radial equation is, remember, d dr, r squared, d big R, d little r, equals L plus 1, big R. Now, we are not going to go through the process of solving this. The most general solution here is big R, some little r function, times a r to the L plus b over r to the L plus 1. And this is assuming that L is some positive number, which we decided we could do with no loss of generality earlier. So let's test to make sure that this is true. Let's take the derivative of r with respect to little r. That will give me a L r to the L minus 1 plus b minus L minus 1 r to the minus L minus 1 minus 1, minus 2 really. And then let's multiply by r squared. So we're going to steadily build up to this left-hand side here. Multiply the whole thing by r squared. That's a times L times r, L minus 1 plus 2, that's going to be plus 1, plus b times minus L minus 1, r to the minus L minus 2 plus 2, that's r to the minus L. And then let's take the derivative of this. So again, a times L, L plus 1, r to the L. Oops, that did not show up. Very sorry. There we go. And now we have b minus L minus 1 minus L, r to the minus L minus 1. And this is L plus 1 times a, r to the L, plus L plus 1 times b over r to the L plus 1. And this is L times L plus 1 of our old friend here. And this was simply our definition of r. And so we get L times L plus 1 as a function of r, which is what we expected to get. So, a little smiley face for us. Good job. All right, let's also look briefly here. So that is our solution for the radial equation. Let's next look at the solution for what's known as the angular equation, which, as you would guess, depends on angles. And in this case, theta, which is the only angle we decided we cared about. This is 1 over sine theta, the derivative with respect to theta of sine theta, d big theta, d little theta, is equal to minus L plus 1 times capital theta. Now I am going to change variables. This is not obvious, and you'll see why we do this in just a minute. I'm going to choose a variable u, which I am going to define as cosine theta. So that means that sine theta, which is equal to the square root of 1 minus cosine squared theta, is equal to the square root of 1 minus u squared. And then I am going to rewrite theta, which is a function of little theta. I'm going to rewrite this as p, which is a function of u. So these derivatives with respect to theta is going to be really a derivative of, whatever you're taking your derivative of. Let's call it f. The derivative of f with respect to u times the derivative of u with respect to theta. This uses the chain rule. Now the derivative of u with respect to theta, let's take the derivative of u with respect to theta. That's minus sine theta. So this is minus sine theta. We can replace here with our value of the square root of 1 minus u squared du of whatever you need to take the derivative of, which we decided to call f. All right, let's plug this into our angular equation. We are going to get 1 over sine theta, 1 over the square root of 1 minus u squared, times the derivative with respect to theta, which is now minus the square root of 1 minus u squared. The derivative with respect to u, of whatever it is we need to take the derivative of, which in this case is sine theta, again 1 minus u squared, times now the derivative with respect to theta, which again is going to be minus 1 square root of 1 minus u squared, du of capital theta, which we are now calling a function p, obviously a function of u, minus L plus 1 times p. All right, so here was our new value. We're going to do some quick simplification canceling here. See also this minus sign is going to come through and cancel this minus sign out front, and I am left with du of 1 minus u squared times the derivative of p with respect to u, which is equal to minus L plus 1 times p. You might recognize this equation, or you may not, but this is what's known as Legendre's equation. And there are solutions to Legendre equation, the Legendre equation, and these are known as the Legendre polynomials. So the Legendre polynomials p sub L, which is a function of u, and these have to do with a polynomial of order n, and this tells us that L is an integer. Now you can solve this using the series type of solution for differential equations, and that's outlined in our book, Pollock and Stump. But I'm going to skip over that and just tell you that the Legendre polynomials are P0 of u is going to be equal to 1. P1 of u is going to be equal to, u. P2 P2 as a function of u is 1/2 times 3u squared minus 1, and P3 is 1/2 times 5u cubed minus 3u, u to the 1, so it's just a u here. My bad. All right, so we can combine all of this together now and write the potential, which remember depends on both r and theta. So we can write v of r theta. Remember that this was big R, a function of little r, times big theta, a function of little theta. So let's plug in what we've learned. We are going to add, create a sum over all possible values of L. So L could be 0 to infinity. And first, our value for the solution for the radial equation, which was a sub L r to the L plus b of sub L r to the L plus 1. A and b, remember, are just constants that depend on your initial conditions. P sub L, which is a function of cosine theta. And this is your general form for the potential. All right, this is generally where I start when I'm solving a problem that depends on potential in spherical coordinates. There's no need to really resolve everything because all your initial conditions are right here in the A and the B. There's one other thing to comment on, and that is the issue of boundary conditions. There are two types of boundary conditions. There's what's known as the Dirichlet, I hope I spelled this correctly, boundary conditions, and that's where you have V at some point, say R equals capital R, equals some value, for example, V0. So you're specifying V directly. And then there's what's known as Neumann boundary conditions. And this occurs when you specify what the derivative of V is going to be at a particular location. So perhaps the derivative of V with respect to little r, and let's evaluate this as r equals, say, A. And this is going to be equal to some value, some constant or a function of theta, perhaps. Slash means or, just so we're not confused here. So for example, why would you consider Neumann boundary conditions? Let's consider one example. Remember your boundary conditions for electric fields. You look back at Gauss's law, and Gauss's law, will tell you, say, in E outer, perpendicular, evaluated at a specific radius, let's call that R, big R, minus E inner, or interior region, evaluated at capital R. So sometimes this is called exterior instead of outer, but again, it doesn't matter. And this is equal to sigma naught over epsilon naught, where sigma naught is a surface charge, and it could be a function of theta. So remember that E is minus the gradient of V, so in the perpendicular direction, E perpendicular is going to be equal to minus the partial of V with respect to R. So I can write this as the partial of V exterior with respect to R, and I'm going to evaluate this at the point that little r equals big R, minus a minus, so that's a plus sign the partial of V interior with respect to r evaluated at little r equals big R. This is equal to sigma naught, which could be a function of theta, may or may not be, we don't know, epsilon naught. Of course, sigma is not a function of r because it is a surface charge, so it's at a specific r. And this is an example of a Neumann boundary condition. All right, that brings us to the end of our discussion of separation of variables for spherical polar coordinates. I will be doing an example problem in class on Wednesday, and I look forward to seeing you all there. Stay safe in the ice.